Okay, we continue our conference, and the next speaker is Alexei Sleptsov, and his talk is Quantum R Matrix, Quantum 6j-symbols, and Eigenvalue Conjecture. You can start, please.
Thank you. Well, first of all, I would like to congratulate Andrei on his remarkable anniversary and wish him good health. My talk is about symmetries of quantum 6G symbols and how to get them from quantum Young-Baxter equation. Actually, I am not going to talk in details about quantum algebra and the Young-Baxter equation. I hope that everyone here is rather familiar with these notions. So just I briefly review this in order to fix notations. So quantum universal enveloping algebra of Lie algebra SLN has a quasi-triangular Hopf algebra structure. So there exists R matrix, and for this algebra defined using standard generators, universal R matrix is very well known and given by formula 1. So we would like to consider this quantum algebra with n-dimensional irreducible representations, which are determined by its highest weights. And all of them can be described by a Young diagram, lambda, which is nothing but a partially ordered set of non-increasing, non-negative integers, which are actually partial sums of highest weights. So let us define the linear mapping R12 on the tensor product of two modules of quantum algebra, V lambda 1 and V lambda 2. Involving the above universal R matrix and permutation operator P as given by formula 2. And then introducing notations 3, we get the famous Young-Baxter equation in the form 4. So now let us for a while, for simplicity, put lambda 1 equals to lambda 2 equals to lambda 3 equals to some irreducible representation lambda. And introducing notations R1 and R2, we get Young-Baxter equation in very short and very nice form. R1, R2, R1 equals to R2, R1, R2. So this is our starting point. Now let us consider the tensor product of two irreducible representations, T mu times T nu, and acting in the vector, in the tensor product of two vector spaces V mu and V nu with the help of a usual coproduct. This tensor product is in general reducible, therefore it can be decomposed into reducible representations by Littlewood-Richardson rule. So on the level of vector spaces, this decomposition is given by formula 6. There are only finite non-zero terms in this decomposition. So representation mu and nu are incoming representations, and rho is irreducible subrepresentations with some repeated summands, actually, in general case. So M is a multiplicity space. That is, it is a vector space spanned by highest weight vectors of the corresponding weight rho. And the dimension of this multiplicity space is equal to the number of repeated summands V rho in this decomposition. If multiplicity space is one-dimensional, then this representation is called multiplicity free. And in general case, of course, M is greater than 1. And we have some multiplicity in this decomposition. Well, now let me recall that from the spectral decomposition of R matrices, R12 acts as a constant map in each subspaces V rho from this decomposition. And if we choose the basis of the highest weight vectors, R matrix becomes block diagonal, where different blocks correspond to different representations V rho with block size equal to multiplicity. Next, we can make it diagonal by a specification of the basis in this multiplicity space, and then each block takes the form of unit matrix times the eigenvalues. So eigenvalues of universal R matrix have an explicit form in terms of eigenvalues of quadratic Casimir operator, which explicitly is given by formula 7 and 8, which are very explicit in terms of Young diagrams corresponding to the representation. Okay, therefore it is possible to diagonalize matrix R1, which acts in the space in the tensor cube of V lambda. To do this, we first need to diagonalize universal R matrix, which acts in the tensor product of the first component and the second component. And then the corresponding decomposition looks like formula 9. So we take the first decomposition between first component and second component. And after that, we multiply it by the third component V lambda from the right and take diction once again. It is clear that matrix R2 is not diagonal in this basis because its universal R matrix acts in the tensor product of second component and third component. And we should consider another decomposition which is given by formula 10. So we first take the decomposition between second and third components, then multiply by the first component from the left and take decomposition once again. Since the tensor product is associative, we have an isomorphism between these two decompositions. And this isomorphism is given by a rotation matrix, which is known in literature as a Racah-Wigner matrix or matrix of 6j symbols. So if we consider quantum algebra and its representation, sometimes people call it quantum 6j symbols. Well, actually, matrix elements of Racah-Wigner matrices in literature are usually called Racah coefficients or recoupling coefficients. And the 6j symbols have a slightly different normalization, which is given by formula 12. But in my talk, this normalization does not play any role, and I'm not going to defer these two notions. Actually, this normalization people use in order to get a very nice symmetry property formulas for 6j symbols, but for us it is not very important right now. So we can express R2 matrix in terms of diagonal R1 matrix and Racah-Wigner matrix, and then Young-Baxter equation takes the form 13. So this equation relates eigenvalues of quantum R matrix and quantum 6j symbols. Well, of course, it is a nonlinear matrix equation, and it is rather complicated to solve it. It is possible to do for a small size of matrix U, but for general case, it is, at least for me, completely unclear how to do it. But still, it is possible to use this equation in order to produce symmetries of 6j symbols. And now let us discuss what is known about symmetries of 6j symbols at the present moment. So values and various properties of quantum 6j symbols are very well known for SL2 algebra, but for higher ranks, much less is known. Nevertheless, some properties and relations for them are known for arbitrary ranks. Let us briefly discuss it. First of all, Racah matrices are orthogonal because it is a rotation matrix from one orthonormal basis to another one. Also, there are very nice so-called tetrahedral symmetries, which are generated by permutations of rows and columns in 6j symbols and are given by these formulas. Let me briefly comment it. Let us consider SL2 case, where all finite dimensional representations are given by one row Young diagrams. let us consider arbitrary such 6G symbol with 4 arbitrary representations. Now, values of these R's are nothing but positive integers which satisfy so-called fusion relations. It means that representation R12 should belong to tensor product of R1 times R2. R23 should belong to R2 times R3. R4 belong to R1 times R2 times R3, and so on. In SL2 case, these fusion rules are nothing but triangle conditions on these numbers. And then it is possible to associate with 6G symbol a tetrahedron, like drawn in this picture. This tetrahedron has 4 vertices, and now we can permute these vertices. And 6G symbol will be invariant under this permutation. And in such a way, we get the tetrahedral group as for SL2 6G symbol. It turns out that now it is possible to generalize these symmetries for arbitrary SLN and for quantum SLN case. And the formula looks precisely the same, just only somewhere you need to use conjugate representations, which for SL2 equivalent to initial representation. Of course, now fusion rules for arbitrary ranks are much more complicated, and it is not possible, at least I don't know how to associate it with tetrahedron, but formula are still same. And they are very nice and very useful in practice. Okay, now let's move further. The next property is so-called the Rakabe coupling rule, which is also a general property for arbitrary quantum SLN, and it is given by formula 18. Actually, I don't need this property in my talk, and let me just skip it. The last one is a famous Pentagon identity. Let us consider tensor product of 4 irreducible finite dimensional representations. And then there are 5 possibilities to decompose this tensor product into reducible representations, which is given by these formulas. And then we can go from, say, decomposition 19 to, say, decomposition 23 by the chain 19, 20, 22, and 23. And also, there is another way given by the chain 19, 21, and 23, using 6G symbols at each step. And then we get a relation between these 2 chains. So it looks like formula 24, and it is famous Pentagon identity or generalized Biden-Harn-Elliott identity. So Biden-Harn and Elliott discovered this identity in 1950s for classical SL2 algebra, but it turns out that this property can be generalized for quantum and arbitrary SLN just in the same way. Okay, now we see that all symmetries can be divided into linear symmetries and nonlinear. In practice, of course, linear symmetries are very useful because they directly relate one 6G symbol to another one. Instead, nonlinear symmetries, it is rather difficult to use. For example, this Pentagon identity, it is nothing but a system of nonlinear equations, and in general case, it is absolutely unclear how to solve it. Well, for SL2 algebra, there is an additional symmetry, which is called Reg symmetry, which was discovered Reg in 1959 for classical algebra. And it looks like the following relation. For SL2, we should add, of course, tetrahedral symmetries, and then we get all linear symmetries given by a group S4 times 3, which contains 144 elements. And this is all known linear symmetries for SL2. Well, Regge symmetry was first discovered for classical algebra after general expression for the 6j symbols was found in terms of hypergeometric function, because symmetries of this hypergeometric function were known explicitly. So in quantum case, the form of Regge symmetry does not change, but only instead of classical function, we should use a co-hypergeometric function. But it remains unknown whether there are counterparts of Regge symmetries for more general case than SL2. And in principle, there are two options possible. It could be that the case of SL2 algebra, due to its simplicity, has increased symmetries. And in more general case, there will be nothing. And all linear symmetries are exhausted by the tetrahedral symmetries. Or in general case, there will be much more symmetries and they will be different and more complicated. Well, actually, at the present moment, we do not know how all symmetries of 6j symbols look like, but we definitely know that the second option is implemented. There are a lot of additional symmetries. And in order to understand it, we need to look closely at equation 13, which relates diagonal R matrix and Raka-Wigner matrix. So recall that we choose the basis in such a way that R1 is diagonal, and it depends on incoming representations lambda, intermediate representation mu, and resulting representation rho. The matrix elements of R1 themselves depend on the eigenvalues of quadratic Casimir operators for different mu, but which particular mu contribute there depends on the fusion rules, which I have already mentioned. So it means that mu should belong to tensor product of lambda times lambda, and rho should belong to lambda times mu. Now let us note that this equation is homogeneous in R2. And therefore, one can ask the following question. Suppose that one can find such rho prime not equal to rho, such mu prime not equal to mu, such that R1 prime is proportional to R1 with some constant which does not depend on mu. Then equation 30 written for matrices U and U prime are the same due to their homogeneity. So we have that U and U prime should satisfy one and the same equation. So looking at this equation, one can put forward the following conjecture, which was formulated by Itayama, Mironov, Morozov, and Morozov Jr., that U prime is equal to U. Well, definitely it is a rather bold conjecture, because equation 30 is a nonlinear matrix equation, and no one promised a priori that it would have a single solution. Moreover, it has a lot of solutions, generally speaking. However, we are only interested in those of them that correspond to rotations of bases in the space of multiplicities of representations of the quantum algebra SLN. So I don't know if this conjecture is true in general case, but I have serious reasons to believe that it is. At least to the present moment, we have not found a single counterexample, but many facts have been found that speak in its favor. And let me list some of them. So we should think about this conjecture as the symmetries of 6j symbols. Namely, if the size of matrix U is equal to the size of matrix U prime, and all eigenvalues of Casimir operators for all mu is proportional with the one and the same constant to mu prime, then U is equal to U prime. First of all, we proved this conjecture for n equals to 2. I mean, for quantum algebra. It turns out that in this case, this condition of the conjecture are equivalent to compositions of Regge and tetrahedral symmetries. For higher ranks, this conjecture is open at the present moment, but we managed to use it to predict new symmetries of 6G symbols, which are completely unknown. I mean, beyond those which I discussed already. And these symmetries, in some sense, will be generalizations of Regge symmetries and tetrahedral symmetries. So let us consider some example. For example, for symmetric incoming representations, the eigenvalue conjecture predicts the following symmetries, which you can see. All of them, if we restrict ourselves to SL2 case, reduce to known tetrahedral symmetries and Regge symmetries. But for higher ranks, it gives us some generalization. Also, we get symmetries for conjugate symmetric representations. These symmetries for n equals to 2 reduces to tetrahedral symmetries. And we get some such very nice example when tetrahedral symmetries can be generalized in a very non-obvious way to the higher ranks, at least for some particular class of 6G symbols. All such symmetries which I mentioned, we have checked for some particular small representations R1, R2, and R3 through the direct computation with the help of highest weight vectors. All these examples are multiplicity-free cases, because it is rather difficult to deal with 6G symbols with multiplicities analytically. But we have some numerical results. So using highest weight approach, we have constructed on computer several hundreds examples of Raka-Wigner matrices for different representations. We did it in order to calculate colored Homfly polynomials, because they can be expressed in terms of R matrices and the 6G symbols. And in that approach that we use, there is a sum over all possible representations. And in order to calculate, we need a lot of 6G symbols. So we developed a very powerful technique to do it, and obtained a lot of particular examples. And it turns out that some of them satisfy conditions of the eigenvalue conjecture. And below, I list some of them just for illustration. The first example is a 6x6 matrix, and it does not contain multiplicity, but now incoming representations are not given by one-row diagrams, it is given by two-row diagrams. The second example is again a 6x6 matrix, but with one double multiplicity. And it turns out that these matrices coincide, and the conditions of the conjecture satisfied. And the last example, the most complicated which we have explicitly, it is a matrix 9x9 with two double multiplicities. Well, it is not all our results which confirm the eigenvalue conjecture, but let me stop here, because to explain other results, I need much more time. To conclude, let me say that it is very interesting and very unexpected, at least for me, that eigenvalue conjecture works in cases with multiplicities, because it is very hard to work with them by analytical methods. And there are not many results in the world literature concerning 6G symbols with multiplicities. So thank you very much for your attention, and congratulate Andrei once again.
Thank you very much. So we have 5 minutes for questions. So please ask if there are any.
Thank you, Kirill.
Okay, if there are no questions, so again, thank you very much.